Hi guys, welcome to our first video in Chapter 15. Chapter 15 talks all about solutions. To begin, we're going to talk about Section 15.1, which introduces many vocab words that we're going to need to discuss solutions and talks about the basic forces at work when we talk about a solution. So for quick initial vocab words, a solution is a homogeneous mixture of one or more solutes dissolved in a solvent. I'm going to highlight homogeneous, right? We talked about that earlier in the year. Meaning evenly dispersed and you can't see the different parts. To dissolve is the process by which the particles of a solid are surrounded by solvent particles due to those favorable intermolecular interactions between the two solvent and solvent particles, right? Intermolecular meaning forces between different molecules. A solvent is the substance that dissolves in the other. This is the majority of the solution. Water is, of course, our universal solvent. The solute is the thing being dissolved by the solvent. This typically makes up the minority in a solution. So I have here an image that shows the process of dissolving in a very rudimentary way. You can see a solid solute is dropped into a liquid solvent, and then the solvent particles interact with those solute particles and pull them away from one another and eventually disperse those solute particles evenly throughout the solution. And what we can see now is a homogeneous mixture. So some characteristics of solutions that we need to talk about. When you look at them, you can't tell the difference between pure substance and a solution because solutions are homogeneous mixtures, right? So visually, you can't tell the difference. Solutions can be in any state, actually. They could be solid, liquid, or gas. We are, of course, going to focus mostly on liquid solutions because they are the type we can control most easily. A good example of a gas solution would be air, right? Maybe like the air around us. And that's a mixture where the solvent is nitrogen, which makes up about 70% of the atmosphere. And oxygen could be considered a solute, right? It's a thing dissolved in that nitrogen. We also have carbon dioxide and we have methane, and we have other pollutants and stuff, but that's a good example of a gas solution. A solid solution could be something like steel, where you have iron forming the solvent, a solid iron, and then you have carbon or charcoal is a natural source of carbon, but you have carbon dissolved in that steel to strengthen it and give it some flexibility. Of course, we're going to talk all about liquid solutions, but I would, I guess, like to point out how carbonated water is a solution where you have a gas dissolved in a liquid, where you have carbon dioxide gas dissolved in liquid water. Anyway, so moving on with our characteristics of solutions, water is our most common solvent, of course. 4 more vocab words that we've heard before, but I'll reiterate just for completeness. Soluble means able to dissolve in a given solvent. Insoluble means unable to dissolve in a given solvent. Miscible refers to 2 liquids that are soluble, and immiscible refers to 2 liquids that are insoluble. Okay, so I want to now talk about solvation in aqueous solutions, right? Like I said, we're going to spend the majority of our time focused on liquid and aqueous solutions because that's where most chemistry happens. So solvation is defined as the process of surrounding solute particles with solvent particles to form a solution. We can see this process very clearly in this image here. I think this is a great image to show us what's happening. If you consider the polarity of a water molecule, remember that the oxygen is more electronegative and therefore will be slightly negative. And the hydrogens are less electronegative and therefore will be slightly positive. So if we have sodium chloride, if we consider that chloride ion, the green one here, this green particle is negative and therefore is going to associate with the positive side of the water molecules around it. You can see that in this orientation here. You can see the opposite orientation of our water molecules around our sodium ions, which are positive and therefore attract the negative oxygen ions. I'm sorry, that negative oxygen end of your water molecules. So in order to form a solution, your solvent needs to actually surround each solute particle like this. And this does show why like dissolves like. Polar compounds can dissolve polar compounds because they have these interactions. Non-polar compounds do not have those interactions and therefore can't interact with the polar solutions like water. This is why oil won't dissolve in water. They have no way to actually interact. Okay, so key takeaway here. Substances are soluble in when the interactions between solute and solvent particles are more favorable than interactions between solute particles. That means that it is more favorable to get this water to chloride interaction as opposed to this sodium to chloride interaction. And because it's more favorable to have the chloride surrounded by water, this drives the process of dissolution. And then again, we have another key takeaway here. These things like star attempt, that was ugly, but so make sure you're writing these down. These are very important here, right? These are the key takeaways for this whole little section. The second one is substances will be insoluble when the strength of solute particle interactions is greater than solute solvent interactions. So in the case of oil and water, oil molecules can interact better with other oil molecules than they can with water. Therefore, oil will not dissolve in water. So aqueous solutions of ionic compounds we'll talk about briefly. Remember, ions dissociate in solution, so you can see that exemplified in our NaCl, which is an ionic compound. And then are each surrounded by solvent molecules. Those solvent molecules orient themselves to interact favorably with each ion, right? That's what we saw in our example here. Now, molecular compounds act a little bit differently, and I have a comparative example here. Molecular compounds do not dissociate in solution, meaning they don't break apart, they stay as one single unit of a molecule. The solvent molecules orient themselves to interact whenever possible. So let's take a look at how this might work, right? Because of course, things that are molecules like sugar, they can still dissolve in water. That's why we can make sugar water, but it just looks a little different than ions dissolving. If we look on the left here, we can see ionic compounds, an ion compound sodium chloride dissolving into water, and you can see that dissociation. You have a purple dot here, you have a green dot here. They are separated and they are surrounded by water molecules oriented so that the favorable dipole is towards the ion. On the other hand, if we consider a molecular compound sugar, we see water molecules kind of sticking to this molecule all over the place. When we look into organic chemistry and start to look at, like, for example, a sugar molecule more closely, and we look at where regions of positive and negative charge would be on that sugar molecule, we would see these water molecules orienting themselves favorably according to that polarity on your sugar molecule. But the key takeaway here is that molecules do not dissociate when dissolved. Ionic compounds do dissociate when dissolved. So let's talk now about some factors that affect the rate of solvation, or how fast does something go into solution. It's of course very important for us to recognize that things dissolve when solvent particles collide with solute particles. A water particle has to hit a sodium chloride particle and actually interact with it. If they're not near each other, they can't interact, right? So therefore, we can increase the rate of solvation by increasing how quickly those particles can interact. And we can do this with three major methods. We can either increase the agitation by shaking, stirring, or otherwise moving around our solution and causing those molecules to physically move around faster. We can increase the temperature, which we know increases the kinetic energy and therefore motion of our particles. Or we can increase the surface area of our solute. Crushing something up or putting in something that's very flat is going to allow water molecules to interact with a greater surface of that solute and therefore dissolve it faster. So moving on, we'll talk what is called heat of solution. Many substances change temperature when they are dissolved. In fact, when some substances are dissolved, most substances will release energy, which tends to feel warm. We've experienced this a few times in lab, so I won't go over it too much. But other substances can actually absorb energy when they're dissolved, and therefore these would feel cold. This is a chemical property that's used to create what are called cold packs, whereas releasing energy is used to make hot packs. I make my sixth graders do this in lab. It's not too crazy, so I'm not sure if we'll get to it in chemistry. Moving on. Heat of solution is defined as that overall change in energy that occurs in the solution formation process. So when you dissolve something in a little bit of water, how much energy is actually released, how much temperature change is caused by dissolving that solute. That solute. Okay. Continuing, let's talk about solubility. Again, solubility. refers to, and here's a vocab word, it refers to the maximum amount of solute that will dissolve in a given solvent at a specific temperature and pressure. Spoiler alert, temperature and pressure can change the solubility of things. That's why we have to have them at a specified temperature and pressure. So when we dissolve things into solution, we can reach what's called a saturated solution. Okay, so a saturated solution, I have these two vocab words down here. A saturated solution contains the maximum amount of dissolved solute for a given amount of solvent at a given temperature and pressure. Okay, so saturated solution can't fit anything else in it. An unsaturated solution is just a solution that has less than the less dissolved solute than a saturated solution. Okay, so saturated has the complete amount, unsaturated, not quite full yet. When we achieve a saturated solution, we, of course, will have some solid on the bottom of our container, and then we'll have the dissolved solute in the solution above or around that solid. When we have a solid in a saturated solution, and this is an example here, we have some crystals at the bottom, we have some dissolved, that crystal dissolved in the solution above, there exists what's called a dynamic equilibrium between the solid and the dissolved solution. And I have that pictured here. A dynamic equilibrium means that the particles are still moving. They're still going from being in the solid crystal into the solution, but they are also going from being in the solution and they're crystallizing onto that solid. So going from aqueous back to solid. So when we have a dynamic equilibrium, this refers to a state where the particles are still moving, but the net flows from aqueous to solid and from solid to aqueous are equal. And therefore, you would have no net change in the amount of solid at the bottom of your container. Again, that is called dynamic equilibrium. Very important for biology, very important for chemistry. So we are going to talk about that more as we go through the year. I have a couple of illustrations here. If you want to take a look, you can compare the solubility of various chemicals at different temperatures. This is, of course, on your reference table. You have solubility curves on your reference table that I'll show you how to use shortly. And then down here, I have just a visual of a saturated versus unsaturated solution. On the top, if I dissolve 30 grams of sodium chloride in 100 grams or 100 milliliters of water, I'll make an unsaturated solution. You can see it's clear, no sodium chloride at the bottom. If I instead use 40 grams of sodium chloride, I would achieve a saturated solution, and I could tell I was saturated because I have a little bit of solid on the bottom, about 4 grams, that remains undissolved no matter how long I leave this. Again, saturated, unsaturated solutions. So let's talk about the last factor for 15.1, the factors that affect solubility. First, we're going to discuss temperature and solubility. Many substances, of course not all, but many substances are more soluble at high temperatures than at low temperatures. This is why we want to put sugar in our coffee when it's hot, not when it's cold, because it's easier to dissolve the sugar. Don't want to forget, but many substances, mostly gases like carbon dioxide, are actually less soluble at higher temperatures. And we can see that actually here on this example here. You can see as my temperature increases, many of these substances increase their solubility, but some of them, like our ammonia, our hydrochloric acid, these actually decrease, and sulfur dioxide, these actually decrease in solubility as temperature increases. Again, the best way you're going to do, you're going to answer questions about this would be to use your reference table to determine the solubility at a given temperature. For example, if I was curious, what is the solubility of ammonium chloride at 70 Celsius? Well, I'd say 70 Celsius, well, here, got ammonium chloride, and I read over and say my solubility is like 62 grams per 100 grams of water, right? So that's how we use this table. Again, this is on your reference table, table G. We can use temperature to create what's called a supersaturated solution. So a supersaturated solution is a solution that contains more dissolved solute than a saturated solution at a given temperature. And that's kind of weird because I said a saturated solution was where you couldn't fit any more solute in your solution. Well, in order to make a supersaturated solution, you do have to heat up the solution and then cool it down slowly and carefully. I'll show you guys an example of this in class. It's kind of cool. What a supersaturated solution looks like and what it can do. Anyway, last little bit, let's talk about pressure. The solubility of a gas increases as its external pressure increases. Meaning, if we consider like a can of soda, if you have a closed container with a lot of pressure, like in a soda bottle, you have typically 3 atmospheres of pressure. Well, you can force carbon dioxide to be dissolved in that liquid, and that is, you call that carbonation. Well, if I open the cap and lower the pressure down to 1 atmosphere, which is regular standard atmospheric pressure, I'm going to stop pushing carbon dioxide into solution, so it's going to start to dissolve. Or I'm sorry, it's going to start to come out of solution, and it's going to start to bubble out. And that's what happens when you open up a can of soda. You start to see that gas escaping, and then eventually all the carbon dioxide gas will escape, and you'll have flat soda. We can describe this mathematically using what's called Henry's law. And here it is. It states that at a temperature, the solubility of a liquid is directly proportional to the pressure of the gas above that liquid. And our formula is S1 over P1 equals S2 over P2, where S is the solubility and P is the pressure. All right, guys, thank you for listening. I will see you guys in the next one.